As we know from Newton's third law of motion, for every action there is equal and opposite reaction. But how much action do we need to get a reaction big enough to actually launch things into space? In order to find this, we use Tsoilkovsky's equation. Here's how to derive it.
Well, the first step is going to be to write an equation for the momentum of the rocket. Momentum equals mass times velocity, but as the rocket goes up, its mass decreases and velocity increases, so we need to take that into account. We do the same for the momentum of the exhaust, only the exhaust velocity is a constant throughout the flight. Thanks to the law of conservation of momentum, we can set P1 and P2 as equal to each other, and then we can just FOIL out both sides. Now this value dmdv is going to be so small that we can leave it out, but by doing so we do need to make the dm negative to account for the fact that the mass is decreasing. Our next step is to do a little calculus by first separating our variables and then integrating both sides from 0 to 1. In this case, 0 represents our starting value right at the moment of launch, and 1 is the final value at the end of the flight once all the fuel is gone. And the final equation we have at the end is the famous Tsoilkovsky's equation, otherwise known as the ideal rocket equation. This value mass original over mass final is the propellant mass ratio, and that's what tells us how much fuel is needed in order for a certain amount of structure to reach the necessary velocity for where we want to send it in space. One thing to note is that this equation does neglect the effects of aerodynamic lift and drag, meaning it doesn't give you a completely precise value.
The equation tells us that in order to reach low Earth orbit, a rocket needs to be 90% fuel, with only 1% of its mass being the payload. Add the factors neglected from the equation, and we end up with something that's more like 96% fuel. Thankfully, with some smart engineering, we can get rockets to the point where they're about 85% fuel, with 1 to 4% being the payload depending on the size of the rocket.
If we look at the space shuttle, it could carry 65,000 kilograms of payload into low Earth orbit, and in order to do so weigh nearly 2 million kilograms total, with approximately 87% of that being fuel. You can see how the rocket's fuel inefficiency makes the cost quickly add up.
Thankfully, there are many ideas being explored regarding making space travel more fuel efficient. For example, the company SpaceX superchills liquid oxygen to make their fuel denser. Aerospike engines are a possible alternative to the traditional bell shape that would enable single-stage to orbit rockets. Various facilities are working on development of rotating detonation engines which use a series of explosions to create thrust. There's also the possibility of using nuclear power, though that is regarded as dangerous. We're also not limited to rockets as our mode of transportation. Ideas have been drawn up for a space elevator that would use centrifugal force to send cargo along a tether from Earth's surface to space. Or we could set up a launch site on the moon and take advantage of reduced gravity for launches to Mars and beyond. Ultimately, it's up to us, as the next generation of scientists, engineers, and innovators, to choose how to go forth. As Konstantin Tsiolkovsky himself said, Earth is the cradle of humanity, but we cannot remain in the cradle forever.